In this video, we are going to go through some of the problems on the 710, 711, and 712 worksheet. I'm probably going to do 3 problems, maybe 4, and just pick the different types of problems that we will see on this worksheet to hopefully help you get through some of them. So I'm going to start with number 3. Number 3 says it says the solubility product constant KSP for calcium hydroxide is 6.5 times 10 to the minus 6 at 25 degrees Celsius. And then part A asks us to write the balanced chemical equation for the dissociation in water. So whenever it asks about the dissociation in water, that means that we are going to start with a solid and then break it down into its ions. So calcium hydroxide is CaOH2 as a solid. These are all equilibrium reactions, so we should know that since it gives us that KSP, that means that it doesn't dissolve all the way. So this is an equilibrium reaction. Some of it will dissolve, but some of it's going to stay a solid. So you need double arrows in there. And that's going to become Ca2 plus AQ plus 2 of the OH minus ions, AQ. All right, so that's part A, just writing the equation. Part B says to write the equilibrium expression. Anytime it asks for an equilibrium expression, that's a K. It could be a general KEQ, equilibrium constant. It could be a KC, where we're in concentration, or a KP, where it asks for pressure. This one is talking about KSP, solubility product constant, because that's what the first line of this problem talks about. So we're writing the KSP expression. So we include our products, the concentration of our products raised to their coefficients over the reactants, but my reactants is a solid, so I leave that out. Solids and liquids stay out. So that's part B. Part C says find the molar concentration for all ions in the solution and the molar solubility of the solution. So the molar concentrations means this Ca2 plus here, this concentration, and this concentration of the OH minus. That's what we're trying to find, is the concentrations of each of those things. And then the molar solubility is the S that we talked about in our notes. So I'm going to find S first. So, whoops, I forgot to switch that back. So KSP is equal to, since I only have one of the Ca2 pluses, we're going to call that S. And then I have 2 of the OH minuses, so we're going to call that 2S. And then because it is squared up here in our KSP expression, we're going to square it here as well. Those are 2 different things, 2 different functions. So we have to do the 2S and the squared. Now if I square 2S, squaring the 2 makes it 4, squaring the S makes it 4S squared. And then I'm multiplying it by this other S. So that's going to be 4S cubed equals my KSP. My KSP was given to us in the problem. It is 6.5 times 10 to the minus 6 equals the 4S cubed. Then I would divide both sides by 4 and then take the cube root of that. So that would give me, let's see, I'll divide by the 4. So 6.5 times 10 to the minus 6 divided by 4 is 1.6 times 10 to the minus 6. And then to get the S by itself, I'm going to take the cube root. If you don't know how to do a cube root on your calculator, I can help you figure that out. Or you can just do 1.6 times 10 to the minus 6 and then raise it to the 1/3 power. That would be the same thing. Okay, so S for this one, if I solve this, is 0.012. So that S, that is your molar solubility. So that's like the second part of this question. The first part of this question is asking us to find the concentrations of the Ca2 plus and the concentration of the OH minus. So the Ca2 plus, if we look back up here into this part of our problem, the Ca2 plus, we replace that with an S. So the concentration of Ca2 plus is S, or this 0.012 molar. For the OH minus, because of my balanced equation, I have 2 OH minuses for every 1 Ca2 plus. That means the concentration of the OH minus is 2S, or 2 times whatever my Ca2 plus is. So I'm going to multiply that value by 2, and I get the 0.024 molar. Okay, so those are my concentrations. I'm going to slide up a little bit more, and I'm going to do part D. So part D says, calculate the maximum mass of calcium hydroxide that will dissolve in 100 milliliters of distilled water. So I am going to start with my volume. I'm going to start with that 100 mils of water. So 0.1 liters. And then I'm going to use my concentration, or my molar solubility that I found up here. That's the concentration that can dissolve in a liter of water. So we can use that as a conversion factor. So I can have 0.012 moles of CaOH2 in 1 liter. And then this question asks for grams. So now we're into moles right now. How do we get from moles to grams? We would need a molar mass. So use your periodic tables and find the molar mass of CaOH2. That's 74.096 grams of CaOH2 in 1 mole. So now my moles cancel, and my answer here is 0.089 grams of calcium hydroxide. Now I'm going to go ahead and do number 8. So number 8 says the solubility product constant, KSP, for barium sulfate is 1.1 times 10 to the minus 10 at 25 degrees Celsius. Will a precipitate of BaSO4 solid form when 210 milliliters of 4.75 times 10 to the minus 2 molar BaNO32 is mixed with 315 milliliters of 0.450 molar Li2SO4? So a couple of keywords that I saw. Will a precipitate form? If it says that, you need to think about Q and comparing it to K. So we're going to compare our QSP to our KSP. Think about what's happening here. We're taking 2 solutions in 2 different beakers, and we're mixing them together, and we want to see if a solution will form. So eventually we are going to write a QSP expression for this equation. So let's start by writing the balanced chemical equation that's going to happen here, or how this BaSO4 is a solid, what that would look like. That might help me write my QSP expression, and then that might help me think about what I need to solve for. Okay, so it's BaSO4 breaks down into Ba2 plus and SO4 2 minus. So if I were writing my QSP, I would have the concentration of Ba2 plus times the concentration of SO4 2 minus. So what this means is that I need the concentrations of Ba2 plus and the concentration of SO4 2 minus in this new solution that I've made. So what I'm going to do first is I'm going to start with the amount of the BaNO32. That's where my Ba2 plus is going to come from. So I'm going to start with the volume of that, which is 210 milliliters, or 0.21 liters. And I'm going to multiply that by its concentration as a conversion factor. So 4.75 times 10 to the minus 2 moles of BaNO32 in 1 liter. And then I can go a step further just to make sure that we understand this piece. I need moles of Ba2 plus. So for every 1 mole of BaNO32, I have 1 mole of Ba2 plus. Now mathematically, this piece doesn't change my answer at all, but it might help you think about where that Ba2 plus comes from. So this I got 0.010 moles of Ba2 plus. So those are the moles that I have. Now to find the concentration of Ba2 plus, we're going to take those moles and we're going to divide it by the total volume of my solution now. So I had that 210 milliliters, or 0.21 liters, and I added it to 0.315 or 315 milliliters. This is going to give me my new concentration of Ba2 plus. So I got 0.019 molar Ba2 plus. I'm going to go ahead, after I do the next part, I'll take this answer and we're going to plug it in here. And that's part of finding my QSP. So now I'm going to do the same thing, but for the SO4 minus. So I'm going to slide up just a little bit and start thinking about the SO4 minus. So I had 315 milliliters, so 0.315 liters of the 0.450 molar, so moles per liter, of the Li2SO4. I only want the SO4, so I'm going to show this step also. There's 1 mole of SO4 minus in 1 mole of Li2SO4. Excuse me. So that's 0.142 moles of SO4 minus. Okay, so now I need to find my SO4 minus concentration. So take your moles, the 0.142, and you're going to divide that by your total volume. So the 0.21 plus the 0.315, or the 210 plus the 315. And I got 0.27 molar here. So now I'm going to take this answer and I'm going to plug it into here. And then I will multiply those two things together, and that will give me my QSP. So QSP is equal to that 0.019 times the 0.27, which gives me a value of 0.0051. Now, compare your QSP to your KSP. So 0.0051, and then look into the problem. The KSP is 1.1 times 10 to the minus 10. That's really small. So my QSP is greater than my KSP. And you don't have to write this out again if you don't want to. It just helps me to remember. Think about the flashcards that I might have, that if QSP is greater than KSP, that means a precipitate will form. We will get a solid here. Now we're going to do number 13. Number 13 is about will a precipitate form if I add this stuff slowly to a beaker containing these ions. So it says, if a 0.5 molar solution of K2SO4 is slowly poured into a beaker containing 0.25 molar barium nitrate and 0.30 molar lead-2 nitrate, so both of those are completely soluble, so those are always going to dissolve in water all the way, at 25 degrees Celsius, what will be the first precipitate to form? And then it gives us our KSPs. So we are going to first find the SO4 minus concentration, the SO4 minus max. How much SO4 minus does it take to make that BaSO4? So I'm going to start with my KSP. And again, if you have to write out the balanced equation to show what is happening here to write your KSP, please do that. If you don't need to and you can just skip right to the KSP, that's okay. Just make sure that you're doing it correctly. Think about the ratio of ions there. This is a 1-to-1, so it is just going to be the concentration of Ba2 plus times the concentration of SO4 2 minus. So I'm trying to solve for this SO4 2 minus. I know my KSP, and I know the concentration of Ba2 plus that I have in this solution. So we're just going to plug those things in and solve for the SO4 2 minus concentration. So my KSP was 1.1 times 10 to the minus 10. And then in the problem, it says that a 0.25 molar barium nitrate. So that means that my concentration of the barium, the Ba2 plus, is 0.25 molar. And we're trying to solve for that SO4 2 minus. So I would just divide both sides by that 0.25. And that gives me 4.4 times 10 to the minus 10 molar. And then we are going to do the same thing, but for the PbSO4. So now we're going to find the SO4 2 minus max. What's the maximum amount I need to get the precipitate to start forming of the PbSO4? Again, if you need to write out the equation, I didn't change colors, but I think that you can follow along. Go ahead and do that. And then think about your KSP. This is again a 1-to-1 ratio, so it's just a Pb2 plus concentration times the SO4 2 minus concentration. We are going to plug in our KSP that was given to us in the problem, and then we are going to plug in the concentration of the lead from the lead 2 nitrate that was given to us in the problem. So our KSP is 1.6 times 10 to the minus 8 equals 0.30 times the SO4 2 minus concentration. Again, we're just going to divide both sides by that 0.30, and that will give me 5.3 times 10 to the minus 8th molar. All right, so now we need to compare these answers. So for the BaSO4 to form, I need 4.4 times 10 to the minus 10 molar. That many moles per liter. For the PbSO4 to form, I need 5.3 times 10 to the minus 8th. So we will reach this smaller value first. That's an arrow. That means that the BaSO4 will precipitate first because it does not need as much of the SO4 2 minus. I know I only said I was going to do 3 problems, but I'm going to go ahead and do number 16 as well, because this is one where we're adding a common ion, and it wants to know the concentration after we add that common ion, so I'm going to go ahead and do this one too. It says the solubility product constant, or the KSP, for Ag2SO4 is 1.2 times 10 to the minus 5 at 25 degrees Celsius. Find the Ag plus concentration and the SO4 2 minus concentration after 0.755 grams of AgNO3 are added to a 500 milliliter saturated solution of Ag2SO4 and equilibrium is established. Assume that the total volume, blah, blah, blah. Okay, so what we're doing, we have this stuff that's already constant, already at equilibrium, already saturated, and then we're adding some Ag to it, some Ag plus. So what we need to do is figure out first how many moles of Ag plus are in the original solution. In order to do that, I need to know the concentration of my Ag plus in that solution. So I'm going to write an equation. We have Ag2SO4 as a solid. That's going to give me 2 Ag pluses, AQ, and an SO4 2 minus, AQ. And then I'm going to go ahead and write my KSP. So it's the concentration of Ag plus squared times the concentration of SO4 2 minus. And I need to know what my concentration of Ag2 plus is. So I'm trying to find this piece right here. So in order to do that, I'm going to find my S, my molar solubility. So KSP is equal to, I have 2 Ag pluses for every 1 SO4 2 minus. So this is 2S, and then I still square it, and then times another S. Just like on one of our last problems that we did this is 4S cubed. So I'm going to have 1.2 times 10 to the minus 5 equals 4S cubed. So divide by 4, take the cube root. You should get S to be 0.014 molar. Okay, so now what this means is that my Ag plus concentration, before I add anything to it, is equal to 2S. So I'm going to take that value that I just found and multiply it by 2. 0.014. And that tells me that originally I had a 0.028 molar solution of the Ag plus. Okay, I need to know how many moles that is in a 500 milliliter solution. So I'm going to take my 500 milliliters and write it as liters, and then use that concentration to figure out moles of Ag plus. In 1 liter. So this is 0.0014 moles of Ag plus. So that's how many moles I had originally. Now I need to think about how many moles am I adding. So it said that I added, I'll write us another note. Find moles of Ag plus added. That's what we're doing now. So it said that we added 0.755 grams of AgNO3. So what I can do is I can change this to moles using my molar mass. So 1 mole of AgNO3 over 169.88 grams of AgNO3. And then for every 1 mole of AgNO3, we have 1 mole of Ag plus. Here I got 0.00444 moles of Ag plus. So now, since we know how many moles we started with, we know how many moles we added, and we know we're still in a 500 milliliter solution, we can find the concentration of Ag plus. So the concentration of Ag plus is those two values added together, 0.014 moles of Ag plus that I had originally, plus the 0.00444 moles of Ag plus that I added, divided by that total volume of 500 milliliters or 0.5 liters. That gives me a concentration of 0.037 molar. Okay. So that's the concentration of the Ag plus. Now we have to figure out the concentration of the SO4 2 minus. So think about what's happening here with your balanced equation. Let's go back up to our balanced equation. I increased this Ag plus concentration by adding some stuff. I added that Ag plus. That's going to cause my equilibrium to shift to the left. So this is going to come down. My SO4 2 minus is going to come down from what it originally was, and I'm going to make some more of that solid. So I have to think about how much is this SO4 concentration going to change. That's essentially what I'm looking for here. Okay, so to find the SO4 2 minus concentration, we are going to think about that KSP again. So KSP is the concentration of the Ag plus squared times the concentration of the SO4 2-. We know our KSP, that does not change. So that is 1.2 times 10 to the minus 5. We know our Ag plus concentration because we just found it. So we're going to plug that in, 0.037 squared. And then that leaves us with the SO4 2- concentration. So we can just do a little bit of algebra here to find that SO4 2-. So square the 0.037, and whatever your answer is there, divide both sides by that. So SO4 2- is going to be equal to 0.0088 molar. So we can compare that to what it was originally. So what was it originally? Whatever our S was up here. So in our original solution, we had 0.014 molar of the SO4 2-. Now it's gone down to 0.0088 molar. So that's going to be it. I hope this has helped a little bit, at least, on some of these problems. We do need to do some other review and stuff tomorrow, but we can definitely talk about some of these and go over them a little bit more if we need to.